Okay, we now begin our next unit here in conceptual physics. Our next unit covers what is called momentum. Prior to this unit, however, in the course, when examining the dynamics of an object, for example, the forces that are exerted upon an object, we always considered the object to be a point. However, at this point, we begin to consider distributions of matter. Before we get to ultimately what is meant by momentum, we have to go through a basic description of how we mathematically describe distributions of matter. We do so based upon a definition, what is called center of mass. I'll define center of mass for the simplest possible examples, and then we'll take a look at a couple of example problems associated with each. I'm going to first of all define center of mass for an arrangement of point masses, and that arrangement will be in one dimension. In other words, along a number line. So we'll begin with an arrangement of point masses in one dimension. So consider, for example, a number line like so. And then let's say here along the x-axis, I have three individual masses. So let's say that right here is a point mass m1, and then relative to the origin, this point mass m1 has a position vector. This position vector I'll draw like so. This is just labeled as x1. And then right here is a second mass, call it m2. And then relative to the origin, we have right here a position vector x2. And then lastly, a third, let's say that right here is an m3. And then relative to the origin, right here is a position vector x3. Okay, the position of the center of mass is a kind of average. It's an example in statistics of what is called a weighted mean. Now, I know you don't know exactly what is meant by a weighted mean, but that's not important for our purposes. Here, ultimately, the position of the center of mass, a kind of average, is defined in the following way. Okay, first of all, we write the position of the center of mass as xcm, where cm obviously stands for center of mass. And then in order to determine where it is, we then calculate the following. First of all, we take the product of each mass with its position vector, and then we add all of those products together. So for example, we're going to take m1 times x1 plus m2 times x2 plus m3 times x3 like so. And then what we'll do is we'll divide by the sum of the masses. So in other words, m1 plus m2 plus m3. Like so. Now this here is just how we define it mathematically, and as you can see, I wrote out each individual term to do so. However, there is a mathematical shortcut for writing a number of terms that are being added together. We use a specific symbol to do so. That symbol is called the summation symbol, and we use the Greek letter capital sigma in order to denote it. So whenever you see this symbol right here, this is the capital sigma. This right here in mathematics is referred to as the summation symbol. So then therefore, I'm now going to rewrite the numerator of the expression in the following way, using the summation symbol like so. And notice the letter I that is being used here. The letter I is referred to as an index. And then the way that you read this is we have here m1x1 plus m2x2 plus m3x3 and so on if we have additional masses. And then we rewrite the denominator using a summation symbol in much the same manner, that is like so. Or once again, the letter I here is referred to as an index. And the way that you then read the denominator of the expression is that we have m1 plus m2 plus m3 and so on if we had additional masses. Once again, this is just a mathematical definition, and these are the symbols that we use to describe that definition. Okay, let's immediately go ahead and take a look at a one-dimensional example. Go ahead and copy the problem down into your notes as I read it here. Find the center of mass of 4 identical point masses arranged in the following manner. I'll draw the diagram associated with this. Each object is separated by 1 meter. So then therefore we have the following. Okay, so here is the diagram associated with that problem. It just looks like this. So here's the x-axis once again. And then we have this first object over here. Here's the second object. Here's the third. And here's the fourth, like so. It says that each object is separated by 1 meter. All of the masses are the same. So then therefore I'll just refer to the masses as m. So I have an m here, here's an m, here's an m, and here's an m. And then let's keep track of the objects by their position vectors. So for example, using a different color. Right here is the position vector of the first object. We'll call it x1. Now keep in mind that all the objects are separated by 1 meter. However, this object is to the left-hand side of the origin. So then therefore I have to make its position negative for that reason. So then therefore x1 is equal to negative 1 meter. Now here's the second object. The second object is at the origin by definition. So then therefore its position x2 is equal to 0. Okay, and then here's the third object. Right here is its position vector, x3. This is just 1 meter to the right-hand side. So then therefore I'll write this as a positive number. So x3 is equal to 1 meter. And then the last object here, object number 4, right here is its position vector, x4. This is a total, however, of 2 meters to the right-hand side. So then therefore x4 is equal to positive 2 meters. And now we just use the definition, we'll write out all of the terms, to find the position of the center of mass. So the position of the center of mass is as follows. First of all, we're going to have m times x1 plus m times x2, which is equal to 0. Well, let me write that in nonetheless. And then plus m times x3. And then lastly, in the numerator, m times x4. We'll fill in the numbers here in just a few moments. And then what we do is we divide by the sum of the masses. The masses are all the same, however, so then therefore I'll write the sum of the masses as 4m for that reason. Like so. Okay, now let's go ahead and fill in the numbers. So the position of the center of mass is going to be as follows. First of all, m times negative 1, like so, plus m times 0, plus m times 1, and then lastly plus m times 2. And then once again divide by the sum of the masses, which is 4m. And now let's go ahead and simplify. This right here is negative m, this right here is 0, and then plus a positive m, which cancels out. And then the last term here is 2m. So then therefore, in the numerator of the expression, I end up with 2m, and then we divide by 4m in the denominator, the m's cancel out, and we're left with 2 over 4, which is equal to 1/2. So then therefore, the position of the center of mass is 1/2 meter. This right here stands for meter. Be careful of that in terms of the units. So where is 1/2 meter? Well, it's right in the geometrical center of this system of 4 point masses. It's just right here. That's the location of the center of mass. So notice that the center of mass is a kind of average. It's averaging out where the masses are in space and the total amount of mass that is present. Last thing to note about this problem before we move on to a two-dimensional example is that notice that it's perfectly fine for the center of mass to be in a location where there actually is no mass. All that's there is completely empty space. Now this is a one-dimensional situation. Let's take a look briefly at a two-dimensional situation. First of all, let me describe to you the symbols that we use to describe the position of the center of mass in 2 dimensions. Okay, so next we'll take a look at a two-dimensional arrangement of point masses. So first of all, in general, for using 3 point masses, for example, we would then begin to describe the situation in the following way. Okay, so here's 2-dimensional space. This is the XY plane, like so. And then let's say that I have 3 objects arranged in space. So right here is M1, right here is M2, right here is M3. Okay, each of these masses has a position vector. If you recall from our unit on kinematics, we always use the letter R to describe the position. So for example, for M1, there's an R1, like so. For M2, there's an R2, like so. And lastly, for M3, there's an R3, like so. We could represent, however, the X and Y components of those position vectors as ordered pairs, just to keep the situation in the diagram as simple as possible. So for example, for M1, it has an X1 here in the X direction and a Y1 here in the Y direction. So then therefore, as an ordered pair, let me go ahead and write the components of this vector like this. And then similarly, for the second object, M2, right here, for example, along the X-axis is an X2, and then right here is a Y2, like so. So there's an ordered pair to describe that. And then lastly, we have M3, right here is an X3, and right here is a Y3. Once again, think of it as an ordered pair. Okay, now in 2 dimensions then, the position of the center of mass will now have 2 coordinates. It will first of all have an X coordinate. The X coordinate of the position of the center of mass is described exactly the same way as it is for the 1-dimensional case. So using the summation symbols, once again, it's first of all the sum of the product of each mass with its X coordinate, and then we divide by the sum of the masses. But now, because this is a 2-dimensional case, we also have a Y coordinate to the center of mass as well. It's defined exactly the same way as it is for the X coordinate, except in this case we're using the Y value, that is the Y coordinate of the position of each individual object. So the position of the center of mass in the Y direction is then therefore the sum, once again we'll use the summation symbol, of the product of each mass with its Y coordinate, and then we divide, once again, by the sum of the masses. If you combine the 2 together, you end up with the most general way in which we describe the position of the center of mass by using the letter R as a position vector. Here's the most general way of writing the formula. The position of the center of mass is written as the product of each mass with its position vector. You add them up, and then you divide by the sum of the masses. This is the most general way of writing these 2 components combined together into one expression. However, when doing an individual example, however, we just separate the components out. We calculate the X component first, and then secondly, we calculate the Y component. So I'll do that once again for a specific example. Let me go ahead and erase the board here, and I need to move my file such that we can take a look at that example. So let me do some erasing here. Okay, I'm going to keep these 2 formulas here for the X coordinate and the Y coordinate because we're going to refer to these 2 formulas here in our calculation in just a few moments. And now here is the problem. Okay, this particular example here is not given in terms of numbers. I'm just going to use some letters here to describe the various positions of the objects. But it's once again finding the center of mass of 4 identical point masses arranged in the following way. What the answer is going to look like is going to depend upon how we define things for this example. So let's define things for this example in the following manner. Okay, I'm going to set up the XY coordinate system like so. And then our 4 point masses I'm going to draw like this. This one here, this here, this here, and this here. Each one of these guys here has a mass M associated with it. Okay, and then let me define some letters here to refer to various distances. So for example, along the x-axis, let's call this distance here A. And then along the y-axis, let's call this distance here B, and also this distance here B as well. That's also the same, by the way, for this object over here on the left-hand side. And now let's go ahead and write as coordinates. We can write the individual components of these position vectors. So for example, starting over here on the lower right-hand side of the diagram, this guy right over here has an x component A and a y component of 0. This guy right here has an x component of A and a y component of B. This guy over here has an x component of A and a y component of 2B. And then lastly, this one over here has an x component of 0 and a y component of B. Like so. Okay, now just look at the diagram for just a moment here and keep in mind that all of the masses are equal. On the diagram, roughly where do you think the center of mass is going to be? Once again, think of it in terms of an average. For example, here along the x-axis, is the center of mass going to be towards the right-hand side of the diagram or towards the left-hand side of the diagram? Pretty obviously towards the right-hand side of the diagram because there's more mass over here than there is over here. But now take a look at the symmetry of this diagram in the y direction. In the y direction, where do you suppose the y-coordinate of the center of mass is going to be? Probably right in the middle of the diagram. So roughly right here on the diagram is where I expect to find the position of the center of mass. Let's go ahead and calculate it just coordinate by using these formulas. So let me do this on the lower board. First of all, for the x-coordinate. Okay, so for the x-coordinate now, what I'm going to do is start over here on the lower right-hand side of the diagram and then just kind of work my way to the left. So we're going to take the product of each mass with its x-coordinate first. So first of all, this m times A plus this m times the same A plus this m times the same A. And then don't forget the one over here on the left-hand side, m times 0 for its x-coordinate. And then we divide by the sum of the masses. There are 4 of them, and they're identical to each other. So once again, for simplicity, it's just 4m. Okay, let's do the math here in the numerator. We have 3ma and then 0. And then divide by 4m. Okay, the m's cancel out, and I'm left with 3/4 a. So 3/4 a in the x direction is to the right-hand side of the diagram, as you probably guessed. And now we go ahead and do the same thing in the y direction. Okay, so now starting over here on the lower right-hand side of the diagram once again, what we do first is we take the product of each mass with its y-coordinate, and then we add it all together. So first of all, I'm going to have m times b plus m times 0, sorry. M times 0. And then the middle one here is m times b. Okay, and then this one up here is m times 2b. And then don't forget the one over here on the left-hand side, m times b. And then we divide by the sum of the masses, which is once again 4m. So let's go ahead and simplify now the numerator. When you simplify the numerator, this term is 0. And then I have mb plus 2mb. There's a total of 4mb in the numerator. And then we divide by 4m. The 4m's all cancel out, and we're just left with b. So the y-coordinate of the center of mass, b, is exactly halfway in between the diagram. So then therefore, if this right here is the x-coordinate and this right here is the y-coordinate, then the center of mass is about right here, as we intuitively guessed a little while ago, where its x-coordinate is 3/4 a and its y-coordinate is equal to b, like so. So once you get used to it, calculating the position of the center of mass for arrangement of point masses is rather simple and straightforward. However, there's actually no such thing as an arrangement of point masses. There is instead only distributions of matter. When it comes to distributions of matter, in some of the more advanced physics courses, you begin to use the methods of calculus to ultimately determine the position of the center of mass. In theory, you can do this for any type of three-dimensional object. So for example, consider this strange-looking green hose that I'm going to use in demonstrations that follow this lecture. In theory, we should be able to set up a calculation involving calculus to find the position of the center of mass of this green hose. In theory, you can do this for any three-dimensional object using calculus to do so. Okay, I'll conclude this lecture here. In the next lecture, we go through the physical significance, the physical importance of the position of the center of mass. I deliver this exact same lecture to all of the physics classes. Yourselves in Conceptual Physics AB, Physics AB, Honors Physics AB, and AP Physics C. You all get the same lecture.